Tonight's speaker is Jo Reeves. She did her PhD at the University of Salford and she now works at the University of Exeter as a postdoc. And she's here tonight speaking to us about the study of human movement, which incorporates technology. So I think I've got everything right there, Jo, I hope. So I'll hand over to you. Thank you, Jo.
Okay, great, thanks. Okay, yeah, so thank you for that introduction, Sarah. So yeah, the talk is something in the way you move, real world applications of biomechanics. So when I was thinking about what to talk about, I thought actually, too often in academia we get bogged down in like publishing papers and just these papers get read by other academics and you feel like, where this is actually making a difference. So I thought I'm going to really focus on where it's actually made some changes in real life and made a difference to sports and clinical activities as well. So before I get into all of that, I'll give you a bit more detail of my background and how I started doing this kind of research. So I went to the University of Bath to do my BSc in sport and exercise science, and Bath's known for its rugby. I picture the rugby there, and it also does a bit of research in rugby related injuries as well. So under the sport and exercise science banner, you have the physiology, which is often concerned about the heart and the lung function of an athlete and how it might change with training. And then you have the psychology about getting people to be more active, how you can motivate people, and the different dynamics, relationships you have between in a team. And then you have the biomechanics, which is often concerned with the technique of an athlete or multiple different things really. So although I came across biomechanics in a sporting context originally, there's a whole field in as I said, clinical applications, also ergonomics in the workplace. And if you actually go to the World Congress of Biomechanics that's held every couple of years in normal times, it's massive as well. There's even like bird biomechanics and sort of flow of blood flow and all sorts of things. So the definition just what I found on Wikipedia is the study of structure and function. And sorry, let's just try and minimize this so I can see what I'm looking at. So study of structure, function, and motion of the mechanical aspects of biological systems at any level, from whole organisms to organs, cells, etc., using the method of mechanics. So we're often looking at motion of the whole body and treating the whole body as a skeleton, but sometimes we look at it at the cellular level as well. I had some colleagues when I worked in Canada who were looking at individual cells that were taken out of people's spines or pig spines and looking at how they'd been compressed with loading. So it's a really broad field. So also while I was doing my bachelor's at Bath, I had a great opportunity to go to New Zealand and work at the Research Institute in Auckland. It was obviously an amazing place, lovely scenery. Got to work with some rugby players and the rugby sevens team, and also help with some data collection in the new lab that they'd recently set up there. And this was my first introduction really to motion analysis, and I was helping my supervisor Kelly Shearing in the running clinic they had there. So this is when a runner has an injury such as Achilles tendon problem or something, and they come in for assessment and get all these little markers placed on their clothing and on their skin, and then they run on the treadmill, and then the data from the video and the motion capture is then used to assess what abnormal patterns might be contributing to injury, and then Kelly would make a recommendation as a physio based on that. So that really sort of got me into the clinical way of thinking. And then after my bachelor's, I thought I wanted to really go down more of this clinical route. And so I initially went to the Free University in Amsterdam, called VU, because they have a good clinical biomechanics reputation. They do a lot of walking related research and great research output, but it turns out the program itself wasn't really what I was after. So I then left that program and went to Liverpool John Moores. And in that time, I did a master's and an internship at Alderhay Children's Hospital. And for that project, we were looking at children who had one leg longer than the other. And these children would often get referred to for surgery to correct the bone lengths, and the surgery would be successful in terms of making these limbs more aligned just in their length, but the children are still walking the way they were before the surgery. So we were thinking, is there something in the structure of the muscles that might explain this? I found that actually before surgery, the scale of the muscles were broadly similar, but that was just part of an ongoing project. But it's just an example of how we also look at structure as well as motion in biomechanics. And then I went down the road to Salford and did a PhD there, and they also have a great clinical biomechanics facility and expertise there. Multiple gait labs, and I was looking in my PhD at the effect of foot orthotics or insoles in shoes on muscles, muscle activity, muscle size and structure, and foot and ankle biomechanics in general. And also in that time, I had another great travel opportunity to go to Canada, to the University of Guelph, and work in a neurophysiology lab there, where my advisor Leah Bent looks at how the sensation of the foot can change movement patterns and affect the feedback that goes to the central nervous system and then influences movement. So we really got the Canadian bug and stayed on for a bit longer, and I went to the University of Ottawa. I was looking at improving the techniques we use to record muscle activity in one lab, and also working in a spine biomechanics lab there. So got a good deal of variety there. And then, as Sarah mentioned, I'm currently at the University of Exeter, but not for too much longer, as it was only a short-term project. And so in that role, I've been looking at trying to develop better footwear for over 55s when playing racket sports, because typically a lot of footwear in the athletic industry has been focused on running shoes, and also in younger populations. So if you're playing something like tennis or other sports with a change of direction, you need different support from your shoes. And so we're interested how the effect of aging and change of direction might coexist there. And so in Exeter, we've got a couple of existing biomechanics labs, and also this new V simulator lab, which is one with a very big force plate, and it's also got virtual reality in it as well, which is quite a cool toy, but we haven't got to play with it yet. It's a bit of a sort of work in progress, but definitely a lot of potential for future research there. And then I've just started at the University of Portsmouth, and I'm going to be looking at developing better sports bras, working with industry partners there. So yeah, quite a lot of diversity so far, but I'm going to try and draw on some of those experiences now. So just as an overview, I'm going to say, what do we measure in biomechanics? And this is by no means exhaustive, but the three main things I say would be motion and forces. So if you're just thinking about walking, as you contact the ground, your heel strikes the ground, if you like, you impart a force on the ground. And because of Newton's law of reaction, every action has an equal and opposite reaction. The ground then imparts a force back on you. So it's this ground reaction force that we tend to talk about and measure. And then we also look at muscle activity, which has played a big part in my PhD and my postdoc in Ottawa as well. And we also tend to look at the two of these together. So how the way the muscles are functioning influences the way we move. And so it's really important to look at all these things together and not just in isolation. So when we talk about motion, we're often considering what's called kinematics. And this is the study of motion, body segments, displacements, and their relation to time. So if we're looking at walking, we tend to more say normalize the time in respect to the gait cycle. So this would be, say, one right heel strike to the next right heel strike. And this gives us an easy way of interpreting what's happening over time. And so in this graph, we've got a knee flexion angle. And in this case, flexion is positive. And the first 60% approximately of the gait cycle is stance. So when your foot is in contact with the ground. And this corresponds to where those vertical lines are. And then the next part of the gait cycle is the swing phase. So as you can see, the knee is the most flex in swing when your foot is not in contact with the ground, which is what you'd expect as your knee is bent as you're walking. Because if it wasn't, you catch your foot on the ground and you trip up. So that's just quite an easy to interpret graph with knee flexion. Other ones get a bit more complicated, but that's a nice little example, I think. And it's also in the sagittal plane. So we look at movement in primarily these three planes. So we have the sagittal plane, which is something like knee flexion and extension. And so this would be operating in that plane of that pink square. And then you have the horizontal plane, which is like twisting of your trunk. And then the frontal plane or the coronal plane, which is viewed from the front. And if you tend to think of like a star jump where your arms and legs are going out to the side. So that would be motion in the frontal plane. Okay, so how do we look at kinematics? So we can do this in 2 dimensions with video, like here. And we tend to look at this in the sagittal and the frontal plane. So from the side, like in this picture, and from the front, it's quite difficult to look at it in the horizontal plane. And we can sync 2 cameras together to do this, to try and explain what's happening in these 2 planes. And this is used qualitatively to give feedback to the performer. So if you're a coach, for example, you can give some feedback to an athlete quite quickly. There's software where you can draw angles and displacement, so changes in a position of something from one frame to another, and that can happen quite quickly. We can also quantify this with something called digitizing, and this is where we would define an angle based on a couple of points on the body. So in this case, like we've got the knee and the foot. So you draw a dot around the knee, and then one around the ankle, and the one that's the toe, and make an angle. In this case, we could be looking at how the foot is contacting the ground. So if we have a heel strike or a forefoot striker, for example, so you do that for one frame, and you click forward to the next frame and draw those 3 points again. So it's quite a laborious process, but it is one way that data is still analysed. And so we get angles out of this, and we can also get some velocities and accelerations as well from that. And then the next way is to do this in 3D, which is getting to use all these cool toys. So this is at the V-Simulators facility in Exeter. And this is for the project I mentioned, where we're looking at changes of direction. So in racket sports, where you've got lunges all around the court. So on the left there, you can see me in a motion capture suit. So we've stuck lots of reflective markers on this black Velcro suit. And the cameras around the room record the motion of those markers and use it to build an avatar, which is on the right. So I'm just going to try and get these playing. They may not go at the same time. So. Stop on there. So this technology is the same equipment and systems that they use to do CGI, so computer-generated images in films. So it's always quite cool to say to participants when you come in that you're like a member of a movie star kind of thing. So this is an example of a case study from Vicon, which is one of the leading motion capture systems, and they have a lot of case studies on their website. If you were to look them up, they've got examples of gaming and films and research as well. So in this picture, they've got someone dressed in the motion capture suit with the markers on, and they're using it to make a peanut with the top hat and getting him dancing and jumping around the room. So quite different to footwear research, but quite a funny example, I think. Right, so what is happening with 3D motion capture? So we have what's called active and passive systems. So when you have those reflective markers stuck on you, they're what's called a passive system. And in this case, the cameras in the lab are sending out infrared light. And when the infrared light hits those markers, it then gets bounced back to the cameras, and the cameras then record that reflected light. Whereas with an active system, there are little battery packs attached to the markers themselves, and then the markers emit the light and the cameras record that light that's coming directly from the markers. And then the system records the coordinates of these markers, and we look at motion in 6 degrees of freedom, which means that we have free rotations and free translations in each plane. So in that sagittal plane, looking at the side, horizontal and frontal, so we can rotate in each of those planes, and we can also move linearly in those planes as well. And then we often want to combine the motion with forces to calculate joint moments or kinetics. And in that picture, this lab in Salford, you can see these rectangular plates on the floor, and those are the force plates. So as the child's walking, that's capturing his motion, but when he touches the force plate, he also gets his force as well. And there are markerless options now as well. As the technology is improving and cameras are getting better, we can actually draw these skeletons and record motion without adding extra markers to people, but it depends on what you're trying to do, how accurate this system is currently, I think. And there are a few other options we can do for in-field measurements. So if we have an athlete running around a track, or even I've had a colleague who's recorded measurements in park runs and given people what's called inertial measurement units. And these have accelerometers and gyroscopes in them, and they can record people like out in the real world, if you like. So this is a big move in human movement research at the moment, is to use a wearable technology. And this example from Vicon, there's the Vicon Blue Trident, and these are even waterproof, so it increases the amount of things you can do with swimming and whatnot. And then finally, I'm gonna just talk about a little bit what electromyography is. So this is when we're looking at muscle activity, and it's about the detection and the recording of electrical signal when a muscle contracts. So your brain is telling your muscle to contract, and it sends a small electrical impulse, and we can record the byproduct of that signal, if you like. So a couple of the big names in the field defined it as the study of function through the inquiry of the electrical signal the muscles emanate. And the way this signal happens is you have a motor neuron that's coming from the brain and the spinal cord, and that will innervate a group of muscle fibers, which collectively is called the motor unit. And we can look at these individual motor unit firings individually, or we can look at a summation of multiple motor units in a muscle to see the global pattern of muscle activation. So a bit more detail here. There's the neuron with the spiky dendrite things, and the signal comes down the axon and branches out into multiple muscle fibers, and this sends a wave of excitation along the muscle, in 2 directions. And then we can record this with a sensor. So that is this one. And then we get a spiky looking signal, which is got positive and negative amplitudes because of the difference in the direction it's traveling. But we will then analyze this, we rectify it and filter it. So in rectification, we make all the negative values positive, and then filter it and smooth it so it's easier to interpret. So by the time it looks like something like this, the amplitude is increasing when the muscle is coming on and it's becoming more active, and then decreasing when it's less active. So again, looking at this muscle, it's called the tibialis posterior over the gait cycle, and this muscle does inversion of the foot. So it's like rolling your foot outwards, if you like. So if you were to sprain your ankle and roll outwards on the outer borders of your feet, that would be like extreme inversion. So this muscle does some inversion as you are contacting the ground initially to control your foot collapsing inwards, and then a bit later on in the stance phase of walking, it inverts again. So it's a lot easier to interpret when you've got it in this sort of linear envelope, and we can look at it just qualitatively, and as the signal's going up and down, we can look at discrete points of how much it's active at certain points, and we can also look at how long it's active as well in terms of the duration of activity. So the sensors we use for this can be put on the surface, such as this Dalsis one. We just record through the skin, but in certain cases we can't do that because muscles are too deep. So if we were to put a sensor on the surface of the skin, then we would pick up muscle signals from the muscles that are above it, not the one that we're interested in underneath. So in this case, we use fine wire electrodes and actually insert a wire directly into the muscle, which is what I was doing during my PhD, because the tibialis posterior that I'm interested in is really relevant for controlling foot motion and foot orthotics, and so it was necessary to use these electrodes, but they generally are not as uncomfortable as you might think. It takes a couple of sort of contractions to get the wire settled in, but then after that, once you've moved around a little while, it's just like normal walking for the most part. So we look at EMG, we look at kinetics, and as I said, this is when the force is acting on the body to produce movement. And these are important in terms of injury risk, because when a structure bears too much force, it leads to injury. So it's not just about the motion of a structure. There's been a lot of talk for far too long about overpronation in running, and it's not just about the movement. We do have some pronation naturally, and it's forces essentially that cause injury, that not just motion. And a variable we look at a lot of the time is something called a joint moment, or torque, and this is the force combined with the moment arm, or the distance from the load to the axis of rotation. So if you think about a muscle acting at a joint in terms of a seesaw, so you have a load here, say 10 newtons, and then the point at which the muscle is attached and it rotates the joint, you would combine this moment arm, or this distance, with the force. So in this case, you'd have 50 Newton meters. So this will be an important variable in a lot of research, such as like ACL loading and ACL injury research. So after going through all about how we measure things, I'm going to then say a little bit about the applications in the different areas. So in sports biomechanics, we tend to think about performance and injury risk. And in performance, we can do these diagrams where we thinking about, firstly, what is the key thing that we're trying to achieve. So in the case of a high jump, it is height over the bar. So then we can split that into takeoff height, flight height, and clearance height. And I think a great example of this was the Fosbury flop that came about when Dick Fosbury came up with this new technique in 1968, where he went backwards over the bar and arched his body and bent his knees. And the biomechanics of this comes from, crucially, by bending its body like that, you can get your center of mass below the bar. So the center of mass is the point where, or your, the mean position of matter in your body, and it's the position where you can consider that gravity acts at like a single point. And if you're just stood upright, your center of mass is somewhere around your belly button, or between belly button and chest. But the position of your limbs can actually change where the center of mass is, and your center of mass can be then located outside of your body. So in this case, the center of the mass is below the bar because of the position of the arms. So the position of the arms and the legs changes its body position at the peak, and it means that you can get higher for a given amount of force that you impart at takeoff. So yeah, that's sports performance. And then we also have injury prevention. And injury prevention used to be looked at in terms of a 4-stage model, and the Van Mechelen model has now been extended by Carolyn Finch in 2006 to include a few more other steps. But they both start off with generally talking about the extent of the problem. So how bad is an injury? How often do people get a certain injury in a sport relative to the amount of times they're doing that sport, or being exposed to a risk? And so it's about the prevalence, the amount of injuries there are, but also the severity as well. So how bad are these injuries when they happen? And then from a biomechanical perspective, we then try and establish why this has happened. So what is the technique that has led to this? How are the forces acting on the person, putting them at risk of getting an injury? And then from this, we can then develop preventative measures, and then evaluate how these preventative measures are working, if they're doing what we expect them to do. And this can be done initially in the ideal scientific conditions, so when you're controlling it in a lab. But then if you're actually thinking about an intervention, you need to think about it in the context of the sport. So how well is it actually being received and implemented in practice, and how effective it is in the context of communication with the coach and the players and that sort of thing. So a great example of this is with ACL injuries in team sports. So the ACL, or anterior cruciate ligament, is often injured with a non-contact method. So it's not through impact with another player, it's through changes of direction, and often sudden, unanticipated ones. And it's thought that this is related to what's called a valgus load, or knee adduction. So in this player here, you can see that they've got quite a bent knee that they're standing on their stance leg. So basically, you can think of an adducted knee, externally adducted and internally abducted, as knock knees, basically. So if the knees are sort of collapsed inwards, that's putting you at risk of getting an ACL injury when you're moving. And so this group in Australia developed this 6-week training program for team sport athletes. And part of this involved putting the stance foot, so this leg that they're standing on in this cutting movement, closer to the midline of the body, and having a more upright posture. So this relates to that moment arm that I was talking about earlier in terms of kinetics. So the force that the player is imparting on the ground as is moving can be the same, but by decreasing this distance, this moment arm, then he's decreasing the torque or the moment that's acting around the joint. And so this was effective in reducing this valgus moment, which is linked with the ACL injury risk. So another example, from sports biomechanics is from the University of Bath, which I'm still proud to. I've been to quite a few universities now, but I'm still proud to be from the University of Bath originally. And there's some research that came out of there that informed the rule changes a few years ago in rugby. So this actually features on a campaign called Made at Uni, which I just came across recently. It's a collection of about 100 different projects that have come out of university research. I think in the UK it may be broader than that. I'm not sure, but it's all about real world impact and how university research has made some differences. So with rugby scrums, 40% of catastrophic injuries come from the scrum. So as I was saying, it's not just about how often injuries happen, it's about how bad they are when they happen. So if a player gets injured in a scrum, it's likely to be quite serious. And so they did some research using video pressure and those inertial measurement units that I mentioned, which you can do recordings out in the field quite feasibly. And this led to the introduction of a pre-bind in the scrum. So instead of the players just crouching and touching the opposition, they bind, and so they're not impacting each other as forcefully as they were before. So that's a good success story, I think. And then on to the clinical side of things, which I said is what's my main interests now. So there are these gait labs around the country. They're the ones in the UK and Ireland. If they're attached to a hospital, they're often accredited with the Clinical Movement Analysis Society, which is where this image is taken from. And you might have a child often with cerebral palsy, some other pathology perhaps, but it's often cerebral palsy. And they might get referred to the gait lab by their consultant or their GP for an assessment. This can inform what treatment they have or what surgery. So they come into one of those gait labs, they have all these markers stuck on their skin and their shorts and what have you, and their motion is recorded and a stick figure is made, and then we get several graphs of what's happening in each of their different joints. So it's a bit of a puzzle to try and to relate what's happening, say, at the knee with the foot. And often it's about not doing a surgery. So it's not just a case of what should we do, but sometimes it's better to not actually intervene, because it's important to actually think about what is causing the initial pathology and what is a compensation. So you might be walking a certain way because of a sort of muscle damage, or you might be adjusting for that. And if you treat the compensation rather than the initial problem, then you can actually make a child worse or anyone worse. And there's this phenomenon called birthday syndrome, where a child has an operation and then they grow a bit, and their dimensions change again, and then they need another operation a year later, and then have some surgery, and a year later they need something else. So sometimes it's better to actually not intervene and see how things change as they develop. But yes, some really interesting applications there. And so well, actually, how often does this actually make a difference? Is it just something that people go through the process? But there's a review that came out recently that was an update of a previous review a few years ago, where so they reviewed the literature, they looked at all these research articles that have been published looking at how effective this gait analysis is in making a difference to patients. And they found a lot of articles. It's just over the last 10 years, but 2,712 articles were included that met all the criteria and quality assessment. And the majority of these were on the technical and diagnostic accuracy and outcome prediction. So this is about identifying what particular parameters or variables of interest can separate patients that are likely to have good and bad outcomes of surgery. But there were also 6 studies and 11 in the previous review that demonstrated that as a result of this gait analysis, changes do get made in treatment plans, and also it increases the clinician's confidence in their treatment decisions and can increase agreement among clinicians. So overall, it is a useful process, and so there's labs like this all around the country. I think in Manchester, probably the closest one is Alderhay Hospital, and Salford, I think, was accredited at one point, but I think a lot of the patients in the Greater Manchester area go to Alderhay if they're a child, and Liverpool John Moores actually is now accredited for a specific type of osteoarthritis patient as well that they see there as well. Okay, and another, going back to Salford. Again, I came across this only in the news last week. So Steve Priest is a researcher at the university, and he's led this research on creating a new treatment for osteoarthritis using concepts from psychology and pain management and also biomechanics. And this has been called cognitive muscle therapy, and it's about retraining people who have knee osteoarthritis in the way they walk. So rather than using just exercises that they've got to do over and over, it's about retraining and using biomechanics to do that, and muscle feedback using EMG. So I think we've got there's a video coming in a minute. So yes, I said integrated psychological informed practice. So this is about initially talking to people about their perceptions of pain and sort of challenging some of these perceptions, like I have knee osteoarthritis, it's inevitable, I'm always going to be in pain, sort of thing. And in the earlier stages of the research, they had these interviews, and then they also get given these instructional videos and biofeedback using EMG. So these electrical recordings, we can use it in our data analysis, but we can also show the electrical signals to patients in real time and help them understand how their muscles are working. So with knee osteoarthritis, if you have too much activity of the muscles around the knee, and muscles that would normally act separately are acting together, we have what's called co-contraction, and this increases the load on the knee, and so it's putting a lot more pressure on the knee than is needed on an injured structure. So I can try and play you a video here of one of the examples. Let's see.
There are 2 main muscles which move the knee: the hamstrings, which bend the knee, and the quadriceps, which straighten the knee. When people who do not have pain walk, these muscles switch on and off in sequence to first bend and then straighten the knee. Research has shown that when people with knee osteoarthritis walk, they often tighten the hamstrings and the quadriceps at the same time, creating unnecessary muscle tension and pressure through the joint. It is important for people with knee osteoarthritis to keep active and walk every day. However, it is also important that the knee is not overstressed during walking. This new treatment has been developed to help people improve the coordination of their knee muscles during walking and other activities, which reduces the pressure through the knee.
Okay.
I don't know about everybody else. I got the audio, but not the video there, Jo.
Oh, did you? Sorry, do you want to try that again?
Same here as well, but
Right.
Yeah.
Okay. Let's see if I can.
There are two main
Can you see it now?
muscles which move the knee. The
Yeah,
hamstrings
got it.
which bend the
Yes.
Sorry about that.
There are two main muscles which move the knee. The hamstrings which bend the knee and the quadriceps which straighten the knee. When people who do not have pain walk, these muscles switch on and off in sequence to first bend and then straighten the knee. Research has shown that when people with knee osteoarthritis walk, they often tighten the hamstrings and the quadriceps at the same time, creating unnecessary muscle tension and pressure through the joint. It is important for people with knee osteoarthritis to keep active and walk every day. However, it is also important that the knee is not overstressed during walking. This new treatment has been developed to help people improve the coordination of their knee muscles during walking and other activities, which reduces the pressure through the knee.
No, don't need to get back to the beginning. Okay. All right, with me again now with the slides.
Yes.
So this program was designed to be delivered by the NHS, which is obviously a time-pressured organisation. So with consultation with physiotherapists and patients, it was important to make it deliverable in a relatively short period of time. So it can be done in 6 sessions now. And yeah, it incorporates movement patterns to being in everyday life rather than doing set exercises, as probably everyone can relate to. You don't always want to do your physiotherapist exercises after a while. So this is about relearning patterns and making it a habit and not something extra to your day. And the initial response has been very positive, and they've had comments like genuinely life-changing, which is amazing. And so they're now going on to doing a larger clinical trial to expand on their initial findings. Right. And then lastly, I've got one example from Ergonomics, so biomechanics in the workplace. And this was a paper from Dr. Brian Graham and some of his colleagues, and he was one of my supervisors in my postdoc in Ottawa and does a lot of research on spine biomechanics, especially in the workplace and with wearable sensors as well. So this study was looking at the effectiveness and user acceptability of a personal loading device in an automotive factory. So you can just see here there's a sort of black strap that's sort of down the back and around the waist, and I think it goes all the way down to the ankles as well. And it was designed to offload the muscles while the workers are bent over for long periods of time in the car factory. And so they used EMG again to evaluate what was happening with the muscles, and also some of those wearable sensors as well to measure things like acceleration of the body. And they did find that there was a reduced EMG activity or muscle activity of the muscles that extend the spine. And this can be related to lower back pain. So it's considered a positive outcome. And the participants said on the whole that they felt that they had to put less effort into the work. So there was lower perceived exertion, and 8 out of 10 of them had a positive opinion of the loading device. Okay, so that's all the examples I had. If you wanted some more, I wanted to go into any more depth, there's now a sports biomechanics lecture series on YouTube from the International Society of Biomechanics and Sports, so ISBS, which is sponsored by Vicom. So this came about last year when the pandemic hit and everyone went to sort of doing things online, and a lot of researchers and members in the community thought about how we can reach a wider audience. And the talks are designed, I think, for an undergraduate sort of first year level, but then there's a variety of them on there, and something I think would be interesting to fair few people, regardless of your backgrounds. They're not too in depth. And then the last thing I just wanted to mention is how it's important to do a lot of research studies with a interdisciplinary perspective. So as I said, that one with knee osteoarthritis, they brought in concepts from psychology and pain management. And if you're developing an intervention, it's often important to consider the user and think about what people are saying that they need, because sometimes we get into the habit of designing something or researching something that we think is a problem and it's not a problem, and so we actually need to talk to the user and find out about what the issues are. So at the University of Exeter, while we're doing these biomechanical studies looking at footwear in the lab, we've also been doing some qualitative work, part of which is a survey to find out what the footwear needs are of adults over 55 who play court sports, so sports like tennis and badminton, and also other team sports that have a change of direction in them as well, like netball and basketball and that sort of thing. So if you're interested in completing that survey, my email address is there. It should take about 15 minutes or so online. So there's just a bit of a shameless plug for our research there. So yeah, that's all I had. Thank you.